We're going to do an example here for mass conservation. And the point of this example is really that, you've learned now a new representation for mass conservation using differential equations. But just because you've used that doesn't mean you should always rely on it. So this problem is a problem you've seen very similar problems to already. And the right way to solve this problem is not to use the differential equation. So let's consider this kind of nozzle situation. We've got some fluid coming in here with a velocity of 0.2 meters per second, entering this back of the nozzle. This diameter here, it says is 4 centimeters. For this diameter here is 4 cm. And then it exits out of a smaller nozzle with a 1 centimeter diameter there. And you're asked to find out what the maximum velocity is. The difference between this and prior equations that we've used or prior systems we've used, is we've assumed in the past, using the Bernoulli equation when we were doing that, or mass conservation on an integral basis, that the exit flow was uniform. And that was an assumption that I told you is, sometimes okay, but is always not true. In this case, we're told very specifically that it's not uniform. So the exit velocity is not uniform. We're told that it is a parabolic exit velocity. So it has uniform inlet velocity. So that says uniform velocity at the inlet, so that's fine. But it has a parabolic outlet velocity. So the question is, how are we going to solve that? We're not going to use, we'll write down the conservation of mass equation that we know. We just found this differential equation, du dx plus dv dy plus dw dz is equal to 0. There's no v at the inlet, and there's not going to be any v at the outlet. There's not going to be any w at the inlet or outlet either. But there is going to be v and w in here, right? So as the flow necks down into that nozzle, we're going to have non-zero w and z components. That's going to cause changes in dw dz, dv dy, and therefore lead to changes in u. So the u is not going to be constant. It's going to change. It's going to change with exposition. And so the fluid is going to change its velocity, and we know that, just from common sense. But that's what this equation is telling you. If there's no change in v, if v is 0 and there's no change in w, then there can't be any change in u. So initially, as the fluid is flowing through here, u is going to stay constant at 0.2. But once v and w become non-zero, then that u can change, and that's what's going to happen. But that's about all this equation can tell us. So the way we're going to have to solve this is the same way we've solved all other mass conservation equations, and that's the point of this. Just because we've learned this equation does not mean we want to throw out our other mass conservation concept for integral flow. So or integral analysis. So in this case, we're back to integral analysis. We're going to look at this as a holistic system, study the inlet and the outlet, and figure out what the flow is. So I'll get you started here. We're going to use m dot in equals m dot out. Of course, we know that has to be true because nozzles can't accumulate mass. So we know that m dot in has to equal m dot out of the whole system. And then we just need a relationship for m dot. Well, we know that m dot can be written as some kind of volumetric flow rate, q dot, times rho, where this, in this case, is volumetric flow rate. One of these annoying, duplicate symbols. That also could be heat transfer. It's not heat transfer. In the context of fluid mechanics, q dot is usually volumetric flow rate. So volumetric flow rate there. So for the inlet, it's pretty easy. Q dot in is equal to the velocity at the inlet, which is uniform, times the area of the inlet. We've seen that many times now. The outlet, of course, is trickier. The outlet, we can't just say that. This is the inlet. The outlet is going to be the integral from 0 to r out of some velocity that is a function of r times 2 pi r dr. So that's the formula you need to use for calculating the outlet volumetric flow rate. The way you see what that is, you have to think about the circle looking like this. This is the outlet. At every position r, there's our radial position, there's a velocity. So the velocity is going to be the same all along that ring. It's axially symmetric. We have no reason to suppose that it isn't. We know that it's parabolic, so it's going to be faster at the middle, slower at the walls. What's the velocity at the walls? Well, the walls are no slip, so the walls are going to be zero velocity. So there's going to be zero velocity at the walls, maximum velocity in the middle, and the amount of fluid that's carried out is whatever velocity is at that R position being carried out through a little strip here that is 2 pi r around, that's its circumference, because that's the definition of circumference on that circle, times its thickness, which is dr. So that's small change in dr. So if I blow that little strip up so you can see it better, it's at some position r here. Here's the position r. This distance, this thickness is dr, and its circumference going all the way around it, circumference equals 2 pi r. So the area of that strip is equal to 2 pi r dr. So that's what this is. This is actually your dA. So it's U times dA gives you your volumetric flow rate. We know that, but that's the representation of dA when you're talking about radial strips. So you got a radial strip there that gives you a dA. Hopefully some of you will see that. It's very, very helpful if you can start to understand where these formulas come from instead of having to memorize them. All right, we know that rho is constant, so we don't have to worry about that. So if rho is constant, that means that Q in has to equal Q out, right? Because that's the mass flow rates have to be constant. The mass flow rate is Q dot times rho, but rho at the inlet and outlet are constant, so we can just ignore rho. We just have to match volumetric flow rates in order to get this to work. So why don't you go ahead now and see if you can solve this. I'll pause here and we'll go on to the next video to get the actual solution.